after enjoying the fifth segment, which was on resolution of vectors, now it's time for the sixth segment, which is about the types of vectors. So now we have come to the segment 6. Okay, this is related to types of vectors. So what are the types of vectors broadly? You can see here, let us start from this side. So first type of vector is null vector. Okay, vector whose magnitude is 0, unit vector whose magnitude is 1, coplanar vectors, two vectors which lie on the same plane, collinear vectors which which are basically on the same line, co-initial vectors, the vectors which starts from the same point, orthogonal vectors, the vectors which are perpendicular to each other, parallel vectors which are parallel to each other, antiparallel, that is which are in the exactly opposite direction. Then comes polar vectors, the vectors whose direction does not reverse on reflection, axial vectors, the vectors whose direction reverses on reflection. We have equal and opposite vectors, equal in magnitude, opposite in direction, and equal vectors which are same in magnitude and same in directions. Okay, so we will get into the details of each of them one by one with the help of diagram. So first let us see a null vector. A null vector has zero magnitude and no specified direction. Example is a car at a rest. Okay, its velocity is a zero vector. The symbol of zero vector is this, 0 with an arrowhead at the top, and graphically it will be represented by a simple dot. Okay, that represents a null vector. Then comes unit vector, a vector having unit magnitude, that is 1. Its magnitude will be always 1 and it will have a definite or specified direction. Null vector has no direction or no specified direction rather, but unit vector will have a specified direction. The example will be a car moving with a velocity of 1 meter per second towards east. Okay, the velocity value is 1. The symbol will be, it will be basically having the symbol of the vector itself with a cap at the top. Okay, this is the cap. It is called A cap. It can be B cap, something like that. So if we have the total vector here, from here to here, this is the vector A. Now it has got some length. Now if we consider a part of this vector in the same direction whose length is equal to 1. Okay, part of the vector which is in the same direction whose length is equal to 1, that is called the unit vector in the direction of vector A, or called the A cap. Then comes the vector which is called coplanar vectors. What are the coplanar vectors? The vectors which lie in the same plane. That is, you can think like two pens which are resting on your table. Those two pens will integrate two coplanar vectors. Okay. For examples, the two vectors A and B lie on the same plane. So this is basically the plane. This surface is the tabletop, you can imagine here. Okay, and we have got three pens out here. One is A, one is B, one is C. So all these three are coplanar if C is on the table. But if this C is like, it is standing vertically, okay, at some angle like this. Okay, if the C will be standing like this at some angle, it is going up from the table. If this is the surface and C is going up like this, and the two other vectors A and B are on the table, then what will happen? This C will not be coplanar with A and B. Okay, so in this diagram, A and B are totally on the table, on the same table, so they are coplanar, but C is like vertically, is like moving upwards, leaving the surface of the table. That's why it is not coplanar with A and B. Then comes the collinear vectors, the vectors that lie on the same line, okay, which basically is one above another. Their lengths will be different, but will be in the same line. The example will be displacement of two soldiers parading one behind the other in exactly same path. So if two soldiers are parading one after another, the soldier who is in front, his displacement will be slightly higher, and the soldier who is behind, his displacement will be slightly lower. So if they are continuing to move with the fixed velocity, that is, their gap between them is constant, they are moving with the same gap, maintaining the same gap between them, then this is going to be the vector diagram. This A will denote the velocity of the soldier who is moving first, and B will be the velocity, or sorry, the displacement vector of the soldier who is moving behind. Okay, so these are the collinear vectors which lie on the same line. Then comes co-initial vectors, which basically starts from the same point, which is the common point here. Those are called co-initial vectors. Then orthogonal vectors are basically two vectors which are perpendicular to one another. This angle is 90 degree. Okay, that is the basic thing in an orthogonal vector. Then comes parallel vectors, the vectors which are of different magnitude but same direction. Okay, the same direction means that the angle that this vector makes with x-axis is same as the angle that this vector makes with x-axis. The angles that they make with the coordinate axis are equal. Anti-parallel vectors are exactly slightly similar but opposite to the parallel vectors. It's like in parallel vectors both of them have the same direction. In anti-parallel vectors they are having exactly opposite direction. They look parallel but their directions are opposite. Okay, so how to measure the angle? So in this case, if this is how we measure the angle, in this case we have to measure from here. Okay, I'm repeating again the diagram. Let me use a thinner pen here, that would be better. Yeah, so if this is basically the angle theta 1 that it makes with x axis, then the anti-parallel vector will make an angle like this. Okay, that will be theta 2. So now if we add this theta 1 and theta 2, okay, if you add this theta 1 and theta 2, then it will be not equal. Okay, theta 1 and theta 2 will not be equal, but rather they will be having a difference of 180 degree. So you can write here theta 2 minus theta 1 will be basically having 180 degree difference. So that makes them anti-parallel. In this case, if this was theta 1, if this was theta 2, in this case theta 1 is equal to theta 2. So for parallel vectors, the angle that they makes with x-axis are equal. For anti-parallel vectors, the difference of the angle is equal to 180 degree because one of them is exactly in the reverse direction. Okay, example will be two cars moving in the opposite direction on a straight road. Then comes equal vectors. Equal vectors are basically having same length or same magnitude and the same direction. Okay, and equal opposite vectors are those vectors which are having the same length. Okay, their magnitudes are equal but the directions are not equal. Okay, so let us see what happens here. Equal vectors. So if this is vector A, if this is vector B, what happens is the directions are equal, magnitudes are also equal. So first let us write about magnitudes. Mod A is equal to mod B. So their magnitudes are equal. Also their directions are equal. So we can simply write vector A is equal to vector B. Okay, this means their directions are equal as well as the magnitude. Now in this case, if we have this is the vector A, this is the vector B, we can write their magnitudes are equal because the lengths are equal. So mod A will be equal to mod B. There is no doubt in that. But vectorially the vectors are exactly in the opposite direction. So we have to write here A vector is equal to minus B vector, or we can write B vector is equal to minus A vector, either of them. Okay, so equal and opposite vectors will follow this relation. A vector equals to minus B, B equals to minus A, and their magnitudes will be equal. But in case of equal vectors, magnitudes are equal, the directions are also same, so A and B are practically the same. Then comes polar vectors and axial vectors. So this polar vector is basically called the real vectors, okay, and axial vectors are called the pseudo vectors. Polar vectors will have a definite starting point and a definite ending point. So all the vectors that we have explained till now are mostly polar. Okay, they start from a definite point and they end at a definite point. In case of pseudo vectors, what will happen? They do not have any definite starting or ending point. Okay, they can start from one point, can start from another point, only their length will be same, but they do not have a definite starting or ending point. Okay, how we'll show that, don't worry. Now polar vectors are the ones which may or may not be associated with a rotational motion. A polar vector is may be present in a linear motion, in a vibrational motion, in a rotational motion. Okay, so polar vectors are practically present in all types of motion. So it is not necessary that there has to be any rotational motion, but in case of axial vectors, these must be associated with some rotational motion. Okay, these originates as a result of some rotational motion. So if there is no rotational motion, axial vectors cannot come into question. Okay, axial vectors cannot exist basically if there is no rotational motion, but polar vectors will exist all the time, no matter whether the motion is rotational or not. Then the important thing comes here is the direction of these vectors does not change under reflection through a mirror. Okay, if these vectors are reflected through a mirror plane in the direction parallel to the vector, means if this is the vector, if this is the vector, here is the mirror plane, I put a mirror here. On reflection, the direction of the vector will be same, okay, in the upward direction only. Now in this case, in case of axial vectors, its direction just reverses. Okay, direction reverses under the reflection of a mirror. So if we have a vector in this direction and we have a plane mirror here, then on reflection, if this is an axial vector, its reflected form will be exactly in the opposite direction. Okay, so in case of polar vectors, through reflection, the direction doesn't change. The mirror should be parallel to the vector. Remember that mirror should be parallel to the vector, then it doesn't change its direction. But in case of axial vectors, if a mirror is placed, the direction of the axial vector totally reverses. Example of the polar vectors are linear displacement, linear velocity, linear acceleration, force, linear momentum, mass. Mass is not a vector, it's my bad. So linear momentum, it can be weight basically. Okay, it's not mass but weight. Okay, so linear displacement, linear velocity, linear acceleration, force, linear momentum, and weight, all these are the polar vectors because they have definite starting and ending point. Okay, now in case of the in case of the axial vectors, what are the examples? Angular velocity, angular acceleration, torque, and angular momentum. Okay, these are all the examples of the pseudo vectors or axial vectors. Now I think it's there is still some doubt how this happens, why the direction doesn't reverse in case of polar but it reverses in case of axial. Let's see this in details. This requires a little more discussion. So as you can see in the in this slide on the screen, that is what I had explained. In case of polar vectors, if the plane mirror, this is the plane mirror here, okay, this is the plane mirror. If the plane mirror is kept parallel to this vector A, the reflected vector is having the same direction, it doesn't change. But here if we have the mirror, this is the mirror out here, and if we have a polar vector, sorry, if we have an axial vector out here, which is the vector A, on reflection through a mirror which is placed parallel to this vector, the reflected vector is in the opposite direction in case of axial vectors. That is the vectors which are associated with rotational motion, those ones direction changes. Okay, these are associated with rotational motion. Okay, in those cases the direction of these vectors changes. Now why this happens, that is the next question. So let us see an example. Okay, polar vectors have definite starting ending point but axial vector doesn't. Let's understand. So as it is seen in this diagram, a body of mass m is rotating in a horizontal plane in a circular path. So let us follow this diagram. This is diagram number 1. Okay, let us have the diagram number 1. So in the diagram number 1, this is a tabletop, this one is a tabletop out here, okay, on which an object is rotating in a circular path. This is the circular path in which this object is rotating. Now let this object be at any point of time be at the point P. Okay, it is at the point P at any point of time. So this is the object, this is the object, it is at this point of time, it is at the point P. So as it is rotating in this direction, this is the direction shown here. So at the point P, it will have a linear velocity which will be acting tangentially, okay, which will be acting tangentially along this direction. So this will be along the tangent, this will be along the tangent of this circle. So the linear velocity is going to be along the tangent. This is the linear velocity. Now as it is rotating in this direction, the angular velocity, there will be an angular velocity also. Why angular velocity? Because the angular position also changes. The particle not only uh, travels in meters in distance, but it also travels in angles, we can say. Okay, initially say the particle was here, finally the particle went to this point, so they have traversed an angle theta in between. So as they have traversed some angle, there has to be some angular velocity. Okay, so the angular velocity and axial vector is an axial vector in this case. V is the linear velocity, which is the polar vector. Okay, the linear velocity starts at the point P and is directed along the tangent to the circle. On the contrary, this angular velocity vector omega, this is called omega, is got its direction we will get by using right hand thumb rule. Okay, so as the particle is rotating in clockwise direction, this omega will be in the upward direction. So as I am seeing from here, sorry, this is in the anti-clockwise direction. So since the particle is rotating in the anti-clockwise direction, in this direction, okay, so the angular velocity will be directed towards the top. Now how we are so sure about in which direction the angular velocity will be? For that we need to understand the right hand thumb rule. So as you can see on the screen, yes, this is the right hand thumb rule. So if we have an object which is rotating in this yellow colored circular path, this blue colored thing is a tabletop, you can say. This circular path is the path of rotation of an object, a small pointed object. This red colored thing is an axis, this black colored thing is an axis. There will be another axis also. Let me draw that. Give me a second. So there will be another axis also. So there will be another axis. This will be, say, the x-axis in this direction. Okay, so this is x-axis, this is like the y-axis, and this is like the z-axis. Okay, so x, y, z. So this rotation is happening in the xz plane, and y is the axis of rotation. Okay, this y is the axis of rotation, and this xz plane is called the, this is the basically xz, this is xz plane, which is the plane of rotation. Okay, now let us say this particle is rotating in this direction. Okay, this is the direction in which the particle is rotating. Okay, if you see from the top, it is anti-clockwise direction as seen from the top of the table. So particle is rotating in this way. Then what we have to do? Think about the your right hand in this way as shown in this diagram. Okay, so you can point your four fingers, these four fingers, in the direction of rotation. Okay, curl your four fingers in the direction of rotation. If you curl your four fingers in the direction of rotation, the thumb will be pointing upwards. Okay, the thumb will be pointing upwards. So that will give you the direction of the omega. That will give you the direction of the angular velocity. Okay, so if a particle rotates anti-clockwise, if you see from the top, then it will be, the angular velocity will be in the upward direction. Okay, angular velocity will be in the upward direction. If seen from the top, it happens in the anti-clockwise direction just by using the right hand thumb rule. As you can see here, this four fingers will be bent in the direction of the movement of the object, and the thumb will be pointing upwards. A reverse situation may occur if the particle is rotating in the exactly opposite direction. It is now rotating in a clockwise direction, say. It is rotating in a clockwise direction. So if this is the direction of, if this is the direction of rotation, what we need to do is, again we need to curl the four fingers of the right hand, then the thumb will point downwards. Okay, if you try, this will be it, that four fingers you have to turn and the thumb will point downwards. Okay, so if you curl the finger, the thumb will be pointing downwards, and this will be the direction of the angular velocity. So if you see from the top, the object is rotating in the clockwise direction, the angular velocity will be in the downward direction. Okay, so if you see clockwise rotating something, angular velocity will be away from you. If you see something rotating something in the anti-clockwise direction, the angular velocity will be pointed towards you. Okay, anti-clockwise means the angular velocity is towards you, clockwise means the angular velocity is away from you, and it will be perpendicular to the plane of rotation, the plane in which it rotates, either upwards or downwards, depending on the sense whether it is clockwise or not. Now, so if a particle rotates clockwise as seen from the top, the direction of the angular velocity will be downwards, and if the particle rotates in anti-clockwise direction, if seen from the top, the angular velocity will be pointed upwards. So here the sense of rotation, whether the particle rotates in the clockwise direction or anti-clockwise direction, is very important to determine the direction of the axial vectors. So that is basically the reason for the reversing in the direction while on a mirror. So as you can see in this diagram here, on the left side, this is the original, this is the object side, we can say, and this is the image side. Okay, and this is the plane mirror out here, this is the plane mirror in the middle. So in the object side, if you can see, if I am seeing from the top, okay, this is the top, I am seeing from here, I am looking from this direction, the particle is rotating in the clockwise direction. Okay, the particle is rotating in the clockwise direction. So what is happening here, at any point P, the linear velocity is in this direction, the linear velocity is in this direction at the point P, and as the particle is rotating in the clockwise direction as seen from the top, the angular velocity will be in the downward direction. Okay, this angular velocity will be in the downward direction. Now, due to this mirror, say the reflection happens. Now let us come to the image side. As this particle moves in the clockwise direction as seen from top in the object side, if we see from top in the image side, the direction, okay, of this rotation will get exactly reversed. Okay, the sense will get reversed. So the particle will be inside the mirror, the image will be rotating in the anti-clockwise direction. Okay, the image will be rotating in the anti-clockwise direction. So if the particle in the object side rotates in clockwise direction, in the image it will rotate in the anti-clockwise direction. Okay, now let us concentrate at the point P where the reflection happened. So at this point, as it is in the anti-clockwise direction, so the direction of the linear velocity will be in this direction, that is towards this direction. Okay, now you can compare this linear velocity on the object side and linear velocity on the image side. Their direction is basically same. It doesn't change. There is no change in the direction of the object of the linear velocity, that is linear velocity is object, and on reflection the direction of linear velocity, that doesn't change. But since in the image side the object is now rotating in anti-clockwise direction as seen from top, the angular velocity will be not omega but minus omega, and it will be in the upward direction. Okay, why minus? Because in the downward side we have considered positive, so in the upward side it will be negative. It can be, you can think of it reverse also. You can write minus omega here and you can write plus omega in this side. It's up to you, that's not a matter. The thing is, on one side it has to be positive and in the other side it has to be negative. Okay, so if omega is in the downward direction, minus omega will be in the upward direction. So see what happens, due to reflection of a rotating object, on the object side it appeared to be in the clockwise direction as seen from top, in the image side it appears to be in the anti-clockwise direction as seen from the top. Okay, so on the object side the angular velocity was pointing downwards, but in the image side the angular velocity is pointing upwards. So the direction of the angular velocity on reflection totally reverses, which is an axial vector, but the linear velocity, which is a polar vector, you can see its direction doesn't reverse. On the image side it is in this direction. What would be the reverse direction if the linear velocity would become in this direction? But that doesn't happen. The linear velocity remains in the same direction, angular velocity changes its direction, basically reverses it. So this is basically the reason why polar vectors doesn't change their direction on reflection through a plane mirror, but axial vectors reverses their direction. Okay, so basically with that we have came to the end of this segment on the types of vectors. The next segment will be on the addition of vectors.